So, we welcome in tonight Thomas Cross, who is currently studying for his PhD at Hull in astrophysics, where he's now branching out into both astrochemistry and astrobiology. He's been recommended by the professor of astronomy there, Brad Gibson. I'm sure a lot of you know it. And if he can say you're good, then you've got something to stand up to, young man. So anyway, with regards to his background, previously as part of his master's, he lived in Svalbard and researched the aurora at the SCAT radar system there. His undergraduate degree, which was integrated with his master's, was done at Aberystwyth University. And after completing his master's, he also worked as a teacher in Hangzhou in China, where he taught English as a foreign language and science. So can please everybody give a warm Mexborough and Swilton welcome to our tonight's speaker, Thomas Cross. Thank you. Over to you, Thomas.
Yeah, thank you for the introduction. I wanted to do a quick disclaimer. I've managed to get a cold before this. So if I'm a bit stuffy or I need to sneeze or something, I do apologize in advance. So I guess I'll just start then. So yeah, can you see my screen okay?
Yes, thank you.
That's fine.
So as you know, Thomas Cross, I'm at the University of Hull, so the EA9 Centre, which is run by Professor Brad Gibson. And I thought I'd do a little outline for today. So the talk's going to be in two parts. The first part is going to be kind of a biosignatures 101. So I'm kind of going to do some background, give you some examples, and then finish with showing a high profile piece. And then part two is I'm going to show you kind of more the technical side of it and basically what I'm doing. So how, we kind of work with it day to day. And we've got a nice picture there as well. So introduce myself, like I said, Aberystwyth Uni, where I went to. My project was optical SETI, so the search for extraterrestrial intelligence. So instead of the classical radar method, we used light sources to see if there was any pulsating messages or anything. And then, my actual project for my master's was in special relativity, but then I was lucky enough to go to Svalbard, which is where we've got that lovely moody photo of me there up in the Arctic Circle. So I was there for about 6 months. And like I said, I was working at the radar system and just watching the aurora. It was absolutely amazing going from a 24-hour darkness to 24-hour light. And then, much of what was already been said, I was an English teacher in Hangzhou. I was also a research support assistant for a while back at my old uni, and now I'm currently at the University of Hull. And my supervisors are Dr. David M. Benoit, Professor Brad Gibson, and Dr. Marco Pignatari. So I've got quite a bit of a broad project. It's actually biosignatures, astrochemistry, and galactic habitability. So biosignatures 101. I thought I'd start with, the classical science textbook definition. So it's any substance, and that can be an element, an isotope, or a molecule present in something such as a meteorite, or it could be what I'm working with, is the planet's atmosphere. And it has to be characteristic of life and can be used as evidence of past or present life. So this is quite a broad statement. So what we have to do is we need to kind of focus it down a bit more and get in between a certain framework. So I'll show you the framework that we use. So there's a catalog by Seeger, Baines, and Pekowski that was first detailed in 2016 called the All Small Molecules Catalog. And basically what this is a very comprehensive listing of all the molecules that go up to a certain size. So their cutoff point is basically if a molecule can have up to 6 non-hydrogen atoms and then add extra hydrogen atoms on, that's the biggest it can be. So typically as well for the biosignatures, we only consider SNOPS elements. So these are your carbon, your hydrogen, your nitrogen, your oxygen, your phosphorus, and your sulfur. There are some exceptions. So you can get halogenated species. So you can and other things such as like you've got chlorine, iodine, and bromine. But really, the diversity in elements for biosignatures, from what we understand currently in this framework, isn't quite as diverse as you maybe would expect. But this is often because of how different elements react. Like you're kind of looking for specific elements that are a bit more stable than others. So here, yeah, there's a series of criterion that need to be fulfilled. So there's a lovely diagram. Don't worry about that. I'm going to modify it. I just thought it's a nice example. So you've got all the small molecules at the top there. And then we have the filters. So as I mentioned, they can only go up to a certain size. This is because every time you increase the number of elements in a molecule, the amount of ones that we have to add to the list is quite exponential. So it just rapidly increases. So when you think about these molecules, we're trying to detect them in atmospheres or on meteorites or comets or whatever. So they kind of need to be stable. So that means they exist as their pure compound. In the order of days, it's usually good enough. They also need to be relatively volatile. So volatility is quite difficult to, kind of define for a molecule. It's basically whether it exists in gaseous form. So if it's a gas at standard conditions, so, you know, your typical temperature, your typical pressures here on Earth. So again, yeah, this was hard to kind of cut off. So what the Seeger, Baines, and Pekowski did was, if a molecule is below 150 degrees boiling point, so the point at which it becomes a gas, that was considered sufficiently volatile. And then we've got our catalog now, this kind of modified catalog of all the biosignatures that we could have. So I've got some examples. I should say, yeah, when I first started my PhD, the number of biosignatures was about 14,000 plus. I believe now it's actually above 18,000. So it's kind of rapidly updating it all the time when they discover, you know, kind of new compounds or new different formations and everything else. So some examples here, you know, got some classic ones: diatomic hydrogen, which is the top left, ozone, which you know is quite prevalent in our atmosphere. You've got ammonia, mid-left, formic acid, mid-right. Bottom left is methanol, and bottom right is ethane. So it's kind of interesting to note that biosignatures, obviously you think of life, so you think kind of, well, what do we give out? We give out CO2, you think oxygen, you think water. So maybe CO2 is not great for you, but oxygen and water are quite crucial for life. But actually stuff as methanol can be big indicators for specific types of life. Because when we kind of, obviously going into this, we have the mindset of mammalian animals, or just animals basically. So you kind of think the basics, but you have to consider other species and types as well that may also produce these molecules. And then, yeah, this is one of the big ones, benzene. Benzene is quite important. In fact, my supervisor, David Benoit, they've been looking at benzene on Titan as a possible indicator of life. So kind of the cracks in the ice crust, when it gives off the water, see if they can detect benzene in the kind of outpour that's coming off Titan. So some caveats with biosignatures. So some of them are great, and some of them we have as biosignatures for sure, but they can be false positives. So there could be a superficial process that is also making it. So these alternate routes could be, it could be geochemical. I believe carbon monoxide can sometimes be a geochemical process rather than any respiration or anything else. Or we could have perhaps like a photochemical process. That's basically where it's interacting with the light. So in fact, oxygen, even though on Earth, the predominant source would be photosynthesis, actually on other different types of planets, it could be from just a photochemical process, so how the light interacts with them, oxygen molecules. Another thing with false positives as well, what can happen is, as I'll show you later with the data, sometimes some molecules, they kind of swamp or mask other molecules, so you could misidentify. So there's kind of a lot of things at play here. Also, we're relatively bound to life as we know it. It'd kind of be a bit silly to try and consider other things because it's, you know, infinite possibilities. So we kind of have to work with what we know. We can vary though, because we do have a pretty good idea on the different types of planets. So like certain planets are more likely to carry oxygen, certain planets are more likely to carry more hydrogen in their atmospheres. So we can see in the diagram here, we've got Earth. So we've got very, very classical biosignatures here. So O2, ozone, water, carbon dioxide. And then we have these different scenarios. You can see how they kind of vary, but there are common links between the different planets. Don't worry about it too much. I'm not going to go into the different hypotheticals for planets today. So how about some recent context? So hopefully some of you have heard of the phosphine potential discovery on Venus. This was kind of the big one. So in about September, I believe, a research group that mainly from Cardiff, led by Greaves, they reported identification of phosphine on Venus, and the amounts that they reported it in were quite like fascinating. It was unknown if it was some sort of new atmospheric chemistry that obviously we wouldn't know about because Venus has very different conditions, or whether it was pollution from unseen volcanoes. Again, kind of probing Venus is very hard because once you get past the upper cloud decks, it's quite high temperature and high pressure, or life. So, I mean, the whole thing was very, very hotly debated. But to give them credit where credit's due, they did do an extensive look into it. And it was more of a scenario, not them suggesting it was life. It was more, well, there's no other option that we can realistically see. I mean, if you want to read the paper, it's about 100 pages long. So it's quite a hefty, well done piece of work. But yeah, like I said, this caused a big dispute. And around about, they had a lot of contradictions. And in November, a lot of people argued that it wasn't true, that in fact, what I mentioned earlier, masking, there was actually a sulfur species that kind of has a similar like data to phosphine. And then eventually they looked back at their data and it turned out that the data that they received from ALMA, so that's the Atacama Large Millimeter Array in Chile, was actually, some of it was incorrect. So once they did a re-analysis, it actually turned out that they still believe, well, it was a tentative belief in phosphine, but the amount of phosphine was a lot less. So kind of like there was more, and you know, kind of the atmospheric chemistry became more likely, or perhaps pollution from volcanoes became a bit more likely. But I mean, the recent thing that I could find was that an international team concluded it to be false. But again, this is still hotly debated, and the team in Cardiff, led by Greaves, is still looking at it. So this is kind of like a very recent, big, high-profile kind of impact that biosignatures have had. I mean, because of the initial paper, well, partially because of the initial paper, 2 new missions were funded for Venus, so they could do flybys and analysis as well. So biosignatures and me. So I get, it's really nice talking about kind of the big, broad ideas and stuff, but it's kind of interesting also to see like what's the actual nitty gritty, what do we work with? So there's one massive problem with biosignatures as a field. So like I said, you've got the all small molecules catalog, they've got the special criteria that they run it through, and you get over 14,000 molecules, which is a lot of molecules to go through. So you think, okay, that's fine. Surely we've got data for them. That's where the problem comes in. A lot of the data or spectra, which I'll go through in a second as well, are either incomplete, they're incorrect, or just completely missing. I mean, I've had a look through it, and kind of like reliable data, there's about under 50 molecules out of those 16,000 plus. So there's a wide gap of just unknown or incorrect. And obviously, you know, we can't really make much progress unless we know what we're looking for. So this is kind of where we wanted to step in. We kind of wanted to address this massive discrepancy between kind of what we have and what we need. So there's two main schools of thought of how to approach this. You can go for your labor-intensive, extremely accurate line lists. So that's basically the type of data that we work with. And you have teams such as Examol, who are down in at UCL, down in London. Or you have Hytran, which is kind of like the industry standard. And these are amazing. Like, they're so in-depth, they're crazy good. I wouldn't even know how to get something that accurate started. But a problem is, I'm not sure for Hytran, but for Examol, I know basically when you go to do a PhD program, they go, here's a molecule, and you work on that molecule for 3 years. Whereas what we're trying to do, what I'm unfortunately trying to get through, is, we need 14,000 plus molecules gone through. We can't really do this really heavy, intensive route. Although we'd like to, it's just not feasibly possible. I think they did like a rough back of the envelope calculations on this. And it turned out it'd probably take 66,000 years, and you'd need to have so many supercomputers running as well to get through this. And that's if nothing goes wrong and everything's fine and all the rest of it. So, okay, so that's not really feasible for what we're aiming to do here. So there's other ways. So you could go kind of like an approximate fundamental model, it's easier. There's nothing wrong with it. It's more simple, it's more effective. It's what a lot of people use. But again, the accuracy, you have a major trade-off. So you've got the speed and everything, but you're contributing to the incorrect data problem here as well, which arguably is more dangerous than not actually having any data at all. So what we want to do is like an intermediate bridge method, kind of take physics from both worlds, push it together, and then see what we can do. I mean, my supervisor hates me describing it like this, but I might as well say, because it's easier to say, it's kind of the rough and ready method. It can do it. Do you know what I mean? It'll get through it. It's not maybe as pretty as Examol or Hytran, but it'll get the job done. Oh, so this is what I mean when I say line lists and spectra. So this is kind of what we work with. It's just basically showing how, so the molecule, so matter, interacts with light, and then how we can perceive it then. So this tends to be just out of the visible spectrum in the infrared spectrum, or you can have Raman as well. But there's a nice little definition there, but you don't need to worry about it too much. So our solution, like I said, the rough and ready method, and we've called it Prometheus because we like to keep everything really humbly named. I've got a nice little picture there. I'm not sure if you know what molecule that is. It's a very important molecule, I presume, for most of you, and that's caffeine. So, I mean, the big one. So yeah, it's an approximate method. It gets the job done. So I use quantum chemistry. So it's a lot of derivations. I've never written so much maths in my life until I started this PhD. Currently, it will only work on a diatomic. So that's only a molecule with 2 elements. So kind of your diatomic hydrogen, or your diatomic nitrogen, or diatomic oxygen, or your carbon monoxide, so CO. But we're working on it. Currently, I'm working on carbon dioxide as well. And it's kind of, it's a funny one because diatomics, they're nice and easy. They're basically 1D. But once you get to triatomics and bigger, you have to consider 3D motion. But once you've kind of done the first triatomic, you can do all the rest of the molecules. So triatomics are your 3-element molecules as well, sorry. And that, if anyone knows, it's on Python and GitHub if you want to look at it. You don't have to, though. I'm not forcing you. Just have to do a little bit of brand placement. So here's a little excerpt from the code. Basically what we do is every molecule you can kind of sum down into a energy curve or surface. These are crazy complex, but it's actually easier than working with other stuff as well. And what the code does is you give me kind of a surface or a curve, I take it, and then from that curve, I can extrapolate specific constants, and these constants can then be used to make the spectra that I mentioned earlier. So what's here, the blue lines here. And yet, kind of as well, one of the added benefits is that we can alter the temperature on it and it will shift. So we can kind of consider not just Earth-like planets as well. For spectra, we can look at other things as well. And we can input external data sets. So we can have a look how we're doing as well. And then, yeah, like I said, it's just the spectra is the main thing that comes out of it. So I've picked 2 molecules to show you here what we've been working on. So I've mentioned carbon monoxide. So it's heteronuclear diatomics. That means that it's different, 2 different things. So you've got the carbon and the oxygen. It's not symmetric, obviously, and it actually has a contested biosignature status as well. So it's some schools believe it's one of the big ones for life because, you know, it could be an indicator of intelligent life because it's incomplete burning, whereas others think that, you know, kind of you have too much carbon monoxide, it's probably not going to be able to sustain life on the planet. Or we can have diatomic or molecular nitrogen. So that is homonuclear. So it's the same elements, symmetric, and that is firmly believed to be a biosignature as well. So I'll try and get through this as well. So these are the kind of like diagrams that we work with when we're looking at molecules. So the green lines, if you can see them so they'll be on the top of each of the diagrams. They're the simple method that I mentioned earlier. The red is our method, so the intermediate bridge method. And then the black and the purple are kind of like the industry standard, and they're always on the flip side of the diagrams. So, I mean, as you can see, our method doesn't do a bad job of approximating where these lines would be. The intensities aren't great, but I mean, that's not a big problem. That's a bit more cosmetic. Currently, that's more cosmetic. But if you look at the simple method, it's often displaced in the wrong place. So you could quite easily misidentify things if you were using this kind of like incomplete or incorrect data because it's shifted in the wrong direction, where it could be a different molecule instead. And yeah, the temperature is just set to an Earth temperature, so about 300 Kelvin. But it takes ages to read in the Hydron exomol data. It doesn't look like it here, but they have so many minuscule lines on here that are like 10 to the minus 31. There's probably about 5,000 entries that I have to read in before I can plot these figures. So how is this useful at the end of the day? Well, the idea is once we've kind of made it to bigger molecules, we can then automate the process. So basically we'll be able to run through the biosignature catalog quite easily. I think we're estimating it about 100 days, maybe to 200 days, which is quite good. And then once we have all this data, we can then take spectra, so the light sources from exoplanets, and we can then vet the exoplanets to see which ones are likely to carry life, which ones are likely not to carry life. And then we can kind of filter them into categories then of likelihood. So I've got a figure here that kind of shows some of the current potentially habitable exoplanets. We could really do an in-depth, very thorough look through each of those to really, really kind of classify which ones are more likely to carry life than others. And then the nice thing about this rough and ready code is that we can, as I mentioned before, when I started the project, there's about 14,000 molecules, and now there's 18,000 plus. We can just keep updating it, and it'll be a pretty simple kind of short time process as well. Or perhaps you can kind of look at it from the flip side. So if we know molecules that would definitely be kind of toxic or kind of hinder life development as well, we could maybe in fact model them and then look at exoplanet spectra and see how kind of hostile the planet would be, kind of leaning it more into the not capable of supporting life category. So it kind of depends on how you look at it. I think I kind of prefer our method. It seems a bit more positive to be looking for signs of life rather than going into this and being like, I'm looking for no signs of life kind of thing. So I'll finish off with some remarks. Hopefully I've managed to communicate here that biosignatures are an exciting and developing area of physics. I mean, one of the big things as well nowadays is it's so cross-discipline. I'm from a physics background, but now obviously I've really branched out into chemistry and I do dabble in biology and maybe even some geology as well, but I don't like to admit that too much. And yeah, we're hoping to answer the question, is there life on other planets? That is the one, you know, the big goal, the one that we're all working towards. And also, it's interesting to consider as well. Kind of, this is what more the geologists do, the ones that work in astrobiology, is finding our own origins to then help us in the search for other life as well. Because I mean, it's kind of understanding, if you consider the chemistry of Earth now compared to the chemistry of Earth when life started emerging, there is differences. I mean, it had, I believe it was higher oxygen levels rather than nitrogen. And that's what contributed to species being much larger than they are nowadays. So it's kind of like, you know, once we truly understand where we came from, we can really help look forwards to seeing other life as well. And then within my work, the future goals, which I mentioned, is an extension to bigger molecules and then automate it so we can get through the entire catalog and get like a nice, lovely data set that hopefully people will want to use. And so thank you so much for having me. Thanks for listening. I hope that wasn't too much. If you want to have a look at my paper, which is coming out soon, the link's there. If you want to have a look, if you want a bit more of a background as well, there's another paper there. It's a bit dense though, but it is a nice little primer into kind of the topic as well. And yeah, once again, I'm at the email center at the University of Hull. So I mean, if you want any more talks as well, feel free to contact us, and I'm sure someone else will give you perhaps a talk on machine learning or perhaps galaxy formation or something else. We've got quite a broad spectrum of people in the department. So yeah, any questions?
Thank you, Thomas. That's really interesting. Could I ask you to stop sharing your screen? Yeah. And we can ask questions. Just while people are thinking of their questions, Thomas, one from me. If there was one molecule that you could actually detect and say, yes, life has produced that molecule, what would it be? And is there one in your sample set?
So it's kind of a complicated one because you kind of need a combination. I think it's quite difficult to just say one specifically because, again, like I mentioned before, it could be coming from a different source. Every kind of molecule has its pros and cons of where it could be coming from. And not necessarily if it's by itself does indicate that it's being produced by life. So it's kind of, you need to have, this is another reason why we're trying to get through everything, is that you really need like a broad picture. Otherwise you're just getting little snapshots. So what you're trying to like interpret is going to be probably incorrect sort of thing.
So out of your molecules, when you get up to your molecule with 6 atoms in it,
yeah,
what are the best candidates? You mentioned benzene ring.
Yeah.
Are there any others?
So actually, we haven't really looked too much. I mean, the catalog's there already. I'm still in the smaller ones currently. But it's kind of ones I found when I did have a look, like a brief look through. They're quite surprising because, again, some of them are toxic, like methanol. And yeah, it's interesting as well because of the size limiter, that there's ones that you would have thought that are, you know, I mean, literal like DNA molecules and stuff. They're a little bit too big. Well, DNA bases, they're too big. So despite them being like a big, major, you know, green flag rather than a red flag for life, is that currently we don't actually consider them because of their size.
Right. Okay. So caffeine isn't one of them then?
No.
It wouldn't be. No. Okay. All right, ladies and gentlemen. I'm looking around for questions. If you, I'd prefer a digital hand, but if you can't find how to do that, then please wave at me. Peter Lloyd, Doncaster Doncaster Astronomical Society. Evening, Peter.
Good evening, Paul. Thank you very much. Thank you, Thomas, for a fascinating talk. Did I understand correctly? You seem to be saying that you can use molecular nitrogen as an indicator of life. Did I get that right?
Mm-hmm. Yeah.
That surprises me. Are you saying the nitrogen in the Earth's atmosphere is the result of life on Earth?
So nitrogen, if I try and remember this correctly,
it's a fairly inert sort of molecule. I would have
yeah,
thought.
it's I'm trying to think of the proper reason why nitrogen is a big one as well. Oh, sorry, yeah. So it's kind of So this is why we think of nitrogen as it is one of the essential ingredients, obviously, for the building blocks of life. Because you kind of need it with carbon and you need it with phosphorus to be able to form nucleic acids, I believe, and proteins. Yeah.
Proteins, yeah.
Yeah. So even though it's kind of inert, and kind of is required in some of the chemistry to then actually get into the more biogenic, so the biological molecules.
So are you saying that if you fail to detect nitrogen, then it doesn't look good for life?
It's not good for life as we know it, I guess.
Yeah.
I'm ever the optimist in that one.
Yes, okay, thank you.
No worries, thank you for your question.
Thank you, Peter. John Leach.
Hi, Thomas. That was an excellent lecture. Really enjoyed it. The slide you put up with the ASM catalogue, and you put some examples.
Mm-hmm.
And I noticed formic acid, simple carboxylic acid. And I wonder why you chose that as an example.
Mainly, I was just trying to see if I can get a spread. It was difficult to get a spread because, again, like I was saying, it tends to be the shops molecules, so it's not too much of a diverse crowd.
Right.
But that's kind of the ones that I'm aware of because we've had a little look at up to so many size. But yeah, it was just a random pick, to be honest.
Right. I thought there might be something extra special about formic acid.
Oh, no. Unfortunately, I haven't got a good story for formic acid. I'm sorry about that.
Thanks. Thank you.
Okay, thank you, John. Catherine. Good evening, Catherine.
Okay. In addition to the presence of these molecules, could you look for the chirality and the proportion that would be away from the equilibrium positions?
Yeah, so one of the ways that some people look at the kind of biosignature thing is, well, it's the belief that obviously you need disequilibrium in the atmosphere to be able to kind of have the conditions to be forming life. So that is one of the key things you'd look for. I'm not sure about chirality. I guess, because the molecules are obviously big enough to be able to look in for that. But I'm not too sure on that one. But definitely for the kind of out of equilibrium, I'm going to go the other way, is one of the big requirements because obviously we have it in our atmosphere as well.
Thank you.
No.
Okay, Catherine. Peter J.
Hi, Thomas. Great lecture. Well done. Congratulations. Just a simple question. Any favourite candidates so far of all the exoplanets? Exoplanets are an interest of mine. I've not really gone down the life that side of things.
Kind of a top candidate. Okay, I'm gonna kind of side answer it. I actually am quite a big believer that there is a possibility that there's life within our own solar system.
Yeah.
I definitely think Titan and Enceladus are possibly big candidates. So you've got these water worlds, so kind of like the ice crust and the water underneath.
Yeah.
And then because of the hydrothermal vents, there's a likelihood that it could sustain life. Because I mean, when I was discussing kind of, understanding our own origins to then find other origins, one of the big possibilities is that because of hydrothermal vents, that's how our life formed as well. There's some other arguments as well that basically life kind of piggybacked off like clay. So the lattices of clay, it was able to learn kind of the structure and shapes that would eventually go to be like a proto proto base for a protein or something. But no, I think I'm not too sure about exoplanets. I guess there's quite a big catalog. I'm not sure if the modified Hipparchus catalog.
Yeah,
that's a good one. But I think I truly do believe that perhaps the moons within our own solar system could harbor something.
I would have thought that the light from the exoplanets will be too weak to give you a reliable spectrum at present with the present telescopes we've got out there.
I think a little bit with the exoplanets is it's obviously when you discover them, they tend to be rather large and rather close to the light source. So they don't typically tend to be suitable candidates.
Conjunctures, basically.
Yeah. And kind of the gravity as well would not really work with how we understand it. And that's kind of a drawback currently in the exoplanet side of things. So there's a potential that there's a lot more Earth analogs. It'd be difficult to kind of spot through like the transit method or wobble method or whatever else.
I think TRAPPIST system is a good one.
Oh yeah, because you've got the tidal lock on the planets as well. Yeah,
and Earth-sized as well. I think there was an article somewhere where they did actually investigate the atmospheres through the transit method, and they managed to rule out them having hydrogen atmospheres. But obviously, you wouldn't expect Earth-sized planets to have hydrogen atmospheres, but they do have some atmospheres. So just I suppose with when we'll get better and better telescopes, you'll be able to pick up what chemical elements are in their atmospheres.
Yeah. The hydrogen one's a good one as well, because it's a reducing agent. That's usually indicated that it's not going to be very good for a lot of species that we need, because we obviously need quite a lot of oxygen-bearing species as well. So yeah, that's brilliant that it's not a hydrogen bearing atmosphere.
Thank you very much.
Thank you for the question.
Peter, I'm still looking around for questions. Roy Dunson.
Yeah, I mean, it's just following up on what Peter has been saying. I was on a talk last night somebody was giving a talk on the James Webb telescope that's due to launch in a while. And one of the things they're hoping to do is to actually take part of the spectra as the transiting planet goes across. Is they're hoping actually to pick up absorption from the atmospheres of whatever's transiting across the star. So that they should be able to pick up certainly some chemical information from spectral lines in that way, as the spectral lines change as the transiting planet crosses the alien star.
Yeah, I mean, JWST is literally going to change the game, kind of like as other missions have done before. I mean, when it eventually launches, funnily enough, when I actually started my PhD, I did apply for a project that kind of relied on it launching about 3 months into me starting. And, enough to say I'm now 2 years through my PhD and it still hasn't launched. So it's probably a good job I didn't get that one. But definitely once that starts, that is going to be kind of like a completely new ball game for us, kind of like the data that we'd get. And this will make this search so much easier as well.
So, Thomas, which telescopes are providing your data sets?
The data sets, as in
for your signatures for the spectroscopy.
So actually, the data we produce is synthetic.
Right. Okay. So you're not comparing them with any actual live data.
So when I mentioned the XML and Hytran, what they do is compare it to like experimental or observed data as well. So then by comparing ourselves to their data, we can kind of see as a benchmark.
Okay. So you're not actually comparing it with live data coming from an actual.
No, not currently. We kind of need to. There's a lot of extra kind of legwork that you need to do with that, because you need to kind of consider the atmospheric composition. And then where I mentioned before intensities being cosmetic, intensities become a real important part of it. I haven't quite got there yet. They're a very, very weirdly difficult area. I've had a look at what we need to do, and it was about 2 solid pages of maths. it was crazy. So I'm looking forward. Yeah, I'm looking forward getting to that one. But at the moment, I'm quite happy where we are.
Okay. And did I see Steve Taylor shaking his fist at me?
Well, I did, but unfortunately, you asked my question.
Oh, that's all right.
Because, I mean, you obviously picked up that they've been using the ALMA array, who you're now saying has probably got it wrong. We wondered, obviously, where else you got your information from.
Sorry, Steve, can you repeat that? My internet kind of went a bit funny.
You said early on in your talk about some colleagues in Cardiff who'd got information via the ALMA array, which may have proved to be incorrect. Because we were obviously asking who else or where else did you get information from, but obviously you don't.
Yeah. So their source was obviously ALMA because it's a pretty reliable one. But apart from that one where they needed to do reanalysis, I mean, the outcome it's still present, but it was not in the kind of the parts per million or trillion that they previously believed. I mean, there's a lot of places that we can get it from. But yeah, kind of the focus of my project currently is more that we want to get through the catalogue, and then we'll work towards, well, hopefully the rest of my career will be kind of actually then using it to have a look against experimental data as well.
Because we had one of the senior astronomers from the ALMA array giving us a talk a few weeks ago.
Oh, amazing.
Yes, an American called Chat Hull, who was very good.
Oh, well, sounds brilliant.
So,
I'm sure it was very good.
It'd be interesting if you were pulling their data to pieces.
Yeah.
Okay.
Nice little civil dispute.
William from Cleethorpes. Good evening, William.
Hello, yes. A very interesting talk. Thank you very much. I suppose it's just really following on from what we've been talking about now, but in terms of sources of information, when you do get past all the theory and all this sort of thing, to be actually looking for where there are spectra, you're talking of vibrational spectra, so and rotational. So presumably you are talking about mainly information from infrared telescopes and things like ALMA with the sort of microwave and submicron stuff.
Yeah. So we're currently totally based in the infrared. So I'm not sure how kind of you have all these different kind of transitions. What we're looking at currently is just the fundamental. So it's kind of an easier one, but you have multiple transitions within the fundamental, but it's one of the lower level ones. So we're not really doing high energy or really going too high temperature. Well, we can do high temperature, but it's not going to be good, basically. So yeah, we're kind of very much, we're in the infrared. We're at kind of more sensible temperatures that, you know, more terrestrial like, and that's pretty much the field that we're working in currently. The hope is obviously we can kind of build it further. Like, I mean, I believe, does high tran go up to about 1500, I think, or something like that? So they can get quite hot, and so can XML as well. It's one of XML's things of being able to get quite high temperature results. I think they recently did, was it sulfur dioxide or something? No. They recently did one that was quite high temperature as well. So that's one of their big aims. But again, you kind of have to pick your battles with this kind of stuff, because if we lean too much into that, we're not going to be able to get through the catalogue like we were trying to plan to.
Okay, thank you.
Thank you, William. I'm looking around for the last of the questions. Ladies and gents, I'm not seeing any. Oh, telling a lie. It's Catherine again. Catherine, come to my rescue.
Well, you mentioned about I could ask any question. Is desert varnish organic? No, is it a shadow biosphere. A shadow biosphere.
Is what? Sorry, was it
Desert
varnish?
varnish.
I'm not sure what the chemical formula for varnish is, so I wouldn't be.
Desert varnish is these. Do you know that you can get like petroglyphs on these like dark brown type of coating on some desert rocks? That isn't well understood, and some people are actually saying that could be a shadow biosphere.
Okay.
So you don't know anything about that?
No, I'm not sure about that one, but that's definitely
okay
interesting.
then. Thank you.
Thank you.
Thank you, Catherine. All right, ladies and gentlemen, I think that just leaves us to give a big mech sprint to an Astronomical Society. Thank you to Thomas Cross. Thank you, Thomas.
Thank you.
Yeah, thank you for having me again. It's been great.